Back in my day, centrifugal pumps was the common used expression, but nowadays you have rotodynamic as an option. I don't like that. Sounds kind of stupid. And kinetic, which I'm warming to because kinetic describes really what happens with this type of pump. You have an impeller, which is powered by a motor or engine, and its purpose is to increase the velocity of the fluid going through the pump. Now, as you add velocity to it, to the fluid, you also are adding kinetic energy. And then, with that kinetic energy having been raised, when the fluid is slowed down, the kinetic energy will be converted to pressure. Note, by the way, centrifugal pumps only suitable for low viscosity fluids such as water or wastewater. Now, if we take this high school equation there, we know if we drop something from the 13th floor of a building, which is about 130 feet above grade, it will hit grade at a velocity of about 91.5 feet per second. Conversely, if we fire something up from grade level at, say, 91.6 feet per second, it will rise back up to 130 feet. The tip speed of a 12-inch impeller at 1750 RPM is 91.6 feet per second, which means the head should be about 130 feet at that velocity. And if you take a look at a pump curve, which we have here, a pump um, operating at 1750 RPM and with a 12-inch impeller, the shutoff head is about 140 feet. So it's very close to what you would think so from that calculation. Velocity turning back into pressure or head. Now, pressure and head are sort of interchangeable. Um, Head is how high is the column from the point you're measuring, and depending on the specific gravity, which with water and sewage is 1, that can be converted by pressure. Now, quick comment, Canada is on System SI, which is metric system with a few other mild variations. So I've properly tried to show both that and American units, which I must admit I'm more familiar with. Like 1 foot of head equates to 0.433 psi. Therefore, 1 psi equates to 2.31 feet of head. The two are convertible. We talked about slowing the fluid down. There's two different types of diffusers. One, a volute, and they have what they call a cut water, where the water splits. Water comes off the impeller, and as we go around, the area gets larger and larger and larger and larger, which slows it down, even though water is being dumped into it, slows it down. And in the discharge, there's also a slight increase, which slows it down, which converts that velocity to pressure. Or we can have a radial type where simply the circumference as we move out gets larger and larger and larger. Normally, you don't have a discharge off that. The radial type diffusers mostly are seen on vertical turbine pumps, which we'll get to later on. Now, one of the things we talk about rotation, pumps are designed and tested with water that is basically not rotating, like a pipe where the flow is nice and even, or coming out of a wet well or whatever. If you find the flow is going opposite the direction of the pump, like in this case here, we've got a pump that is rotating clockwise, pardon me, counterclockwise, and the flow is also rotating clockwise. If they're going the same, the pump will underperform, okay, because it's not adding very much. So you find you don't get as much head, therefore not as much capacity as you expected. Nice thing is the power drops off. If it's the opposite direction, in other words, the flow is spiraling in a clockwise direction and the pump is rotating counterclockwise, then the pump will overperform. It'll add more pressure, more head, but also require more power. So all of a sudden, overload becomes a distinct problem. I have seen that. This is an interesting little thing that kind of is based on that theory. You've got a submersible pump which is rotating clockwise. If you look down, you can see the cut water just below the motor. And if it goes around in behind, it gets larger and larger. And as it comes in view, larger still and a bit of a nozzle. And that pump is rotating clockwise. But it's in a sort of a wet well at the bottom that when the level is down, like it shows it here, there's a clockwise flow induced. Now remember, clockwise rotation and clockwise rotation of the pump and clockwise rotation of the flow mean that the pump can't perform as well. So what the intent is, when the level's up high and all this stuff at the bottom is flooded, then the pump pumps like you would expect it to, as per the curve. But as it gets into this situation where you've got this swirling action, the pump will underperform and therefore pump at a lower rate. Therefore, you don't often have to actually turn the pump off because its performance will match whatever the inflow rate is. Kind of a cute little trick like variable speed without. Now, some equations that are very useful. Efficiency and horsepower. And in system SI, we're talking liters per second for these equations, head in meters, specific gravity water sewage 1, and efficiency as a decimal. In US units, what I've memorized, efficiency is capacity gallon, US gallon per minute times head times specific gravity, which is 1, over a constant 3960, and efficiency as a decimal. So with that, you can either get, knowing the horsepower, you can get the capacity and pressure, you can get efficiency, or flip the efficiency and horsepower and calculate horsepower. Now, pump curves are really just the plotting of an output head. Basically, what a manufacturer will do, here's a pump operating at 3550 RPM. They'll start off with an 8.5, the full diameter that you can get, 8.5 inch. And they will test that pump using a calibrated motor, which is a motor which has been on a dynamometer, and they know the current at every load applied to that motor. Therefore, by knowing the current, you know what the horsepower output of the motor is. Using a calibrated motor and measuring head and flow rate is at zero, of course, zero flow rate's easy, but as you move out, they calibrate the point, and you can calibrate, know what the horsepower is from the motor, and from that know what the efficiency is, and therefore draw that curve that you see for that 8.5 inch impeller. Then they'll take and trim it and run the same set of tests at 8 inch, 7.5, 7, a collection of different trims right down to the minimum, which is 5 inch diameter. The interesting thing is, like if you have a 7 3/4 trim on the impeller, diameter trim, it will be right dead between 7.5 and 8. So you can plot that curve and see what it'll do. That allows you, if you want, to actually have a pump that's trimmed for the operating point you want, or trimmed to take maximum advantage of the horsepower you want, or not go into overload. We'll get into that later. It gives you all that kind of flexibility. So, and this is called an oak tree curve because it looks like you've taken a chunk of an oak tree and cut it through, and you've got all the different growing lines on the thing, okay? Now, if you add pumps in series, because each one adds pressure, the pressure will be added. If you add two identical pumps in series, the discharge of one into the inlet of the other, it will double the pressure. Flow stays the same, but double the pressure. Usually, you see that being done with multi-stage pumps like vertical turbines, which have a radial diffuser design, which lends itself very good to that type of system. Now, parallel construction, of course, is basically the flows just add up. Series, I mentioned, one pump into another. By having individual pumps, and it has been done, can be done, one pumping to another, that will work, although you get into the question, what happens if one of those pumps fail? So the control system and everything else has to be looked at with caution, okay? Operating pumps in parallel, as I say, is no big deal. Now, quickly we will look at system curves. A system curve is basically, first off, a plot of the hydraulic grade line, which is easy to find because you know what the elevations are. Then we throw on top of that the friction as the flow rate goes up. So you get kind of a hooked curve. Now, big beware, static head is easy to determine. Friction can be a not very nice word. And most people actually end up over-calculating or overestimating friction and throw in a bit of a safety factor. That's why pump manufacturers like to see operation per the design point to the left of best efficiency, because that magic friction can disappear or minimize itself quite a bit, and all of a sudden you're operating further out than what you thought. Um, if variably spun comes to operate, you really want to find out what the minimum maximum speeds are where you're going to operate. Now, combining the system curve and pump, take a look at this. You've got a single pump curve, you've got a static head, and to which friction has been calculated. So a single pump will operate at about halfway between best efficiency point, the little arrow, and full runout. Put two pumps in parallel, the head doesn't change at any point, but the capacity doubles. So you see, with two pumps operating, based on the calculated curve, we're almost at best efficiency. With three pumps, we're nicely to the left. Boy, that looks good. Then you get it out in the field, and you find out the actual system curve is much flatter. There isn't that much friction there. So one pump, you're way off to the right. Two, you're still the wrong way. Maybe only when you get three and the flow rates are high are you getting something reasonable. So often, it's a very common thing where what was estimated and what actually happened are two different stories and problems and create. And of course, talking single pump curve, if you do pump in two pumps in series, it doubles the head, capacity stay the same, doubles the head, and three stages or three in series will give you the third situation. Okay? Now, let's talk about vortexing. If you have a bathtub or sink full of water and you pull the plug, you will notice as the level gets down, it will start to swirl counterclockwise in North America, if you've seen the Simpsons episode where Bart forms Australia. And eventually it'll go down to the point, well, a pump will do the same thing. And as the pump is sucking, and you can get that cone of air coming down to the point where the pump is actually getting that air inside it. When it does, it gets noisy. It's called snore. And you find a distinct drop off in performance. Now, when that performance drops off, very often the drop in flow is enough that the vortex will cease. It'll go back up to nice level surface, and there's no problem again, but it will reform itself. The way to eliminate or minimize the chances of vortexing is to add what they call a suction umbrella, which is basically a plate that's increasing the area seeing the inlet. So at the tip of the plate, the surface or the velocity, flow velocity down is much, much, much lower than what it was without that umbrella. This picture is kind of interesting. It's a drainage pump at an angle, and in fact, that column at the top right there carries off. The pump shaft is inside that. At the top, there's a motor with a belt drive to the shaft because these pumps run very slow. And you can see that a vortex has formed, and obviously air will very quickly be going into the pump. Now, case situation. Anytime you see purple, it's a war story of mine. Pump station on the island, Vancouver Island, had a 150 horse pump and a pair of 230s. And in a wet well designed to recommended manufacturer standards. Inside was an adjacent below valve chamber. And if you're in the valve chamber, after a period of time, you'd start hearing a growling sound. It would suddenly quit. And then a few minutes later, you do the same thing all over again. If you looked at the wet well surface, after a time, a vortex would form that would slowly get larger and larger and larger over several minutes. Air is now going into the pump, causing the growling, until suddenly it would stop because the pump had so much air it choked on it and was unable to pump. Then it would clear itself of air, start pumping again, and the cycle would repeat itself. Now, let's talk cavitation. Cavitation is not vortexing. Cavitation is the fact that fluid will boil at virtually any temperature if the pressure is reduced enough. For example, at 5,000 meters elevation, something like 18,000 feet, atmospheric pressure is half that at sea level, and water will boil at only 80 Celsius compared to 100 Celsius at sea level. In fact, in the 19th century, explorers obtained rough approximation of elevation by measuring the temperature at which water boiled. Now, when pressures get low enough in a pump or valve with flow rate, they get low enough, you get cold water boiling, which is cavitation. And of course, the warmer the water, the earlier that will occur. For example, condensate, which is steam from a boiler or whatever, as steam is condensed, that liquid condensate is very hot and it doesn't take much drop in pressure to get it to boil. Now, cavitation by itself is not a problem if the bubbles reform as the pressure goes up away from anything, right in the liquid itself. In other words, you create a little bubble of vapor, but when the pressure comes back, that little bubble will turn into a much smaller drop of liquid, and the bubble will then collapse. So you get it, it gives it a very gravelly sound, very much like vortexing, but real gravelly sound. And the only effect, again, is it chokes flow, much like vortexing does. But different from vortexing. If those little bubbles, vapor bubbles, happen to be up against metal, any part of the pump, when they collapse, it's like a little ball peen hammer. It's a fairly distinct little thing, and the higher the pressure, the worse it is. Although the higher the pressure, less chance of vortexing. Anyway, when that happens, it will attack the metal, and you can see, with some pumps in a matter of hours, most pumps, a matter of weeks. I've seen valves, 6 months, you'd look like the thing had been, somebody had gone at it and tried to cut it in half. So it's quite a dangerous little concern in terms of the life of the pump. As I say, it is not a result of air being drawn into the pump. In fact, introducing a small amount of air to the pump inlet, either being drawn in and inlet pressure is atmospheric or injected, will dramatically minimize cavitation, as that air will fill the voids created by cavitation once you've got aerated water. Up to about 0.9% air can be used in some applications to eliminate the effects of cavitation. There was a pump station in Vancouver that had cavitation issues, and they actually did have a compressor that was putting in small amounts of air. And the effect of that is very dramatic, by the way. Instead of growling like hell, virtually the pump will go silent when you get that air in there. However, air entrainment, even in amounts of 1 to 2%, can cause the pump performance to drop dramatically. If you've got a pump that's got a suction lift, for example, and with the pump not running, you can see water leaking out, a pinhole leak, just say drop, drop. When the pump is running, that can let in enough air in a lot of cases that the pump simply quits pumping. So suction lifts are very rough. You got to be so careful that there is no leak of air whatsoever. Now, what they do for cavitation, pump manufacturers have the pump with a rated NPSHR, net positive suction head required. Now, this is an absolute value. Therefore, with atmospheric pressure, will give you that pressure in terms of head, and let's talk US units, 34 feet. So to the NPSH available that you need, you can add that atmospheric pressure on. Like, take a look at this pump here. From the center line of the pump to the liquid is 1 meter. But because the atmospheric gives you sort of 10 meters free, you've actually got 11 meters available. The pump curve, you look at it and says NPSH required is 7 meters, so you got 4 to the good. You're not going to have any serious problems. Now, let's talk thrust. Radial and axial. Radial is at right angles to the shaft. Axial is in line with the shaft. Now, you can see with a volute type pump, where the cutwater is, at zero flow is when you get your worst axial thrust, roughly in that direction and fairly high. At best efficiency point, it's virtually dead opposite the cutwater and quite a bit lower. And at 150%, you can see the direction and the amount. On a end suction pump where the shaft is cantilevered out to the impeller and you've got 2 bearings, obviously the forward bearing, the one close to the impeller, is seeing the effects of that thrust. If you have a double suction or split case pump, and we'll get into those later on, where basically it's like 2 impellers back to back, and a shaft at either side, that pump can handle axial thrust much better. And by the way, radial thrust, and axial thrust is virtually killed because the two impellers are back to back, which is a single impeller, but it's like two back to back. Now, radial thrust in a pump can be minimized by adding a second cutwater wall, as you can see here, which is at 180 degrees from the basic casing cutwater. That's fine, but those are tricky to cast and therefore expensive. Now, axial thrust, what forms axial thrust with an end suction pump? The fact basically that you've got low pressure on one side of the impeller, and on the back side of the impeller you've got high pressure from discharge, which is shown in red, and there's an area where you've got low pressure at the front, high pressure at the back. That tends to thrust with that blue pump casing to the left. It tends to want to pull it away. Now, there is a way around that to help mitigate it. If you take a look at the two drawings below, you can see the one on the left, low pressures in green, high pressures high, and you can see the difference. There's a difference where you've got high pressure on the left and low pressure on the right, and you've got that thrust on that drawing to the right. Now, if we put in a set of wear rings and then bleed holes on the back of the impeller, so there's a distinct pressure break at the same point there is on the inlet, then the two areas calculate even out. The backside of the impeller below that is seeing the same as seeing inlet pressure. Therefore, there's minimal axial thrust. Little comment on impeller design, just of general interest. The wider the impeller, the flatter the curve. The less twist to the impeller vanes, the flatter the curve. The more vanes, the flatter the curve. Just things of interest. More significantly, the larger the inlet, the more gallon per minute. We also see that with the large inlet, you get lower NPSH required. So condensate pumps handling boiler condensate very often have really big inlets to lower the NPSH required. Now, flow range of a pump. A centrifugal pump or kinetic pump will always be happiest when operating at the best efficiency point, BEP. Fluid within the impeller will tend to recirculate within the vanes as flow rate is increased or decreased, creating noise, cavitation, and with volutype diffuser, excessive radial thrust. The sensitivity of pump to operating depends with the size. As they get bigger and number of vanes decrease, like sewage pumps are notoriously bad for this, it becomes a bigger concern. In other words, you're more limited on how far you can operate away from BEP. The general rule is plus or minus 50% of BEP for sewage pumps and large pumps. ANSI says preferred operating range 70 to 120%. Now here's a little drawing where somebody said, yeah, that's good, but best practice would be minus 10 to plus 5% of best efficiency, which is wonderful if you can do it. But if you've got varying conditions and the pump has to operate further on its curve, then that probably is not your option available. Better practice, minus 20 to plus 10, and good practice, minus 30 to plus 15. Again, that's wonderful if you can do it. The better, the better. And it shows you the effects of what happens as you move away from best efficiency point. But a sloppy quick rule is plus or minus 50%. Don't go beyond that, and certainly not with solids handling pumps. Now, you want to be a pump expert, you need to learn the affinity laws. They're very important, okay? Which basically is just taking the fact that head varies as the square of speed, pump speed, divided by 2g, gravity. Therefore, head varies as the square of speed. Double the speed, you get 4 times the head. The flow point or flow area varies directly with pump speed. So if you've got a point on a pump curve, if you double the speed, you double the capacity at that particular point. And as power is a product of both pump head and capacity, power varies as velocity cubed. And these laws are very accurate and certainly more than good enough for day to day. A sometimes quoted fourth law is that NPSH required varies as the square of velocity, but I'd use that with some caution. Better if you can go to the manufacturers. Now, if you have a pump curve at a given rotating speed, you can plot a new curve by simply picking several points on the given curve and applying the affinity laws to get what those points would be at that different speed. For example, now this one's easy at point A, shut off, because the capacity doesn't change its speed, because there is no flow. So you're really just plotting the fact that the head varies as the square of speed. So you can have point A, change the speed, A. Okay, same thing with B, is we slow it down the first step. The head drops significantly because of the change in speed, the square of it, but the capacity only drops directly with speed. You put that point. And if you do the same thing with C and D, then you can plot a curve at a different speed. This one has actually got the original speed plus 3 lower speed. So what you end up creating effectively is a variable speed oak tree curve. And if you don't have one from the manufacturer, you can calculate your own. Now, interesting, because the affinity laws relate to speed, and part of what creates speed is not only the velocity of the impeller, but the diameter of the impeller. You also can say that basically head will vary as the square of diameter, and capacity directly with diameter, and power is the cube of diameter, approximately, because it does affect the flow design of the impeller as you trim it. Cheater formulas. At 1800 RPM, pump head is equal to impeller diameter in inches squared. In other words, a 12-inch impeller at 1800 RPM will be about 144 foot at shutoff within about 5% accuracy. What is very useful is best efficiency point. If you don't know much about the curve, the best efficiency point is going to be about 85% of what shutoff head is. Like 144 feet, 0.85, best efficiency point will be somewhere around 122 feet. If you can again get the curve fine, if you have to take a wild guess, there's how you do it. One of the things, what happens if a pump is operated backwards? And that happens more often than you'd think. You can see the green star, that's the pump curve with the proper volute and the proper speed. Now, it's unusual, very rare to get the wrong impeller with the wrong volute. It is not that uncommon to find that the pump is rotating backwards, particularly with three-phase motors. It's very easy that they're hooked up and it's actually running the wrong way, and what's wrong with the pump? You can see the pump will still pump, but you can see the head curve, the pump curve that's created operating with the impeller going backwards. The capacity's gone way down, the head has gone way down, and of course, very low power. So if you run into that situation where a pump doesn't seem to be performing properly, right off the bat, is it going the right direction? Now, one of the things with pumps, very often you're operating in a cyclic situation, pumping out of a wet well or pumping into a reservoir or hydropneumatic tank, which is essentially a reservoir. Then you're turning the pump on and off based on the levels. Pump cycling does not occur if there's no flow into the wet well. Obviously, you don't have to worry about anything. Does not occur when the flow into a wet well or the reservoir equals the pump operating flow rate. You will find the maximum cycling will always occur when the flow rate into a wet well or from the reservoir is half the pump operating flow rate, half Q. That's where you get your worst cycling, is when the flow into a wet well or out of a reservoir is half what the pump is nominally pumping. To give you a drawing what we're talking about here, let's say you've got a sewage wet well or something, done it in brown for a reason, where the pump would start, where the pump would stop. The volume between those 2 points is the active volume. You need to have that volume to give you the proper cycling rate. Or if you're pumping into a reservoir, between the start level and the stop level, okay? Now, the recommended active volume is based on this equation. Pumped volume per hour divided by the constant 4 times starts per hour. Maximum allowable starts per hour. Now, what are the maximum allowable starts per hour? You get different people giving you different opinions. Based on what I've seen from several people and having talked to a lot of people, these are my recommendations, which I would use and I'd suggest you use. The maximum for centrifugal pumps, kinetic pumps, maximum starts per hour up to a 15 horse motor, 20 starts per hour. 20 to 30 horse motor, 15 starts per hour, which is what Flight, Xylem, recommends for everything. I think they're pushing it a bit. But anyway, on the big stuff. 40 to 50, I would reduce that 10 starts per hour, and 60 to 200 horse, 6 starts per hour. Beyond 200 horse, boy, you're going to, do some serious talking to manufacturers. Any single phase motor, I would restrict. These values should be halved if you're using solid state reduced voltage soft stopping, which we get to into electrical, because it's only used with three-phase motors. You are playing with that motor operating at reduced voltage for a period of time. So it's hard on the motor. You want to have these numbers if you're using solid state reduced voltage starter. Now let's take an example of this thing. If we're pumping 19 liters per second pumping capacity and I've got a 20 horse pump, there's our formula. 19 liters per second times 60 gives you liters per minute, times 60 again gives you liters per hour, divided by 4, the constant, and 15 starts per hour, which is what is recommended for a 20 horse motor. That means you have to have 1,140 liters between start and stop levels. Okay? That's it for this.